recording this. And we are in 9-1. So there's a lot of these little problems that we're going to do. I know it seems like a lot, but they're going to go pretty quick. First thing that we're doing is talking about arranging. We're arranging 5 books on a shelf. If you are arranging things, there's like 5 different spots for it. 1, 2, 3, 4, 5. Actually, I'm going to pause right now. Drew, if this isn't too much for you, you can just pull the desk into the hallway. Or is it too loud in here? It's fine. Okay. All right. Okay, so I'm arranging books in a line. So I've got 5 books and I've got 5 spots to arrange it. I'm going to do or think about what options I have. So for the first book, I have 5 total books. So I've got 5 options I can pick. Once I picked that book, though, I can't use it again. So now I have 4 options for the second book. Once I pick that book, I only have 3 options for the third spot. Once I pick there, I only have 2 options for the last spot. And once I pick those, I only have 1 choice left. I only have literally 1 book left, 1 option for this last spot. I'm arranging these books in a line. And when you arrange them, you're going to multiply. These are all like opportunities that are happening. All of these are possibilities of an event happening. So we've got 5 choices, 4, 3, 2, 1, etc. I'm going to multiply them all together. 5 times 4 times 3 times 2 times 1 is 120. Okay, that's how many options, that's how many ways I can arrange 5 books on a shelf. Now, what if I said, okay, you have 20 books on a shelf you need to arrange? Well, then we would have gone 20 times 19 times 18 times 17, blah, 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 all the way down. Now that's a lot to start writing in my calculator. It's not insane, but like 20 times 19 times 18, that's going to take a long time. I'm going to teach you a shortcut right now because sometimes we're not going to do something easy like 5. We're going to go to like 100 or 200 or 11 even. Like that's a lot more than what we have right here. When you do something like this, a number and then times every number substantially behind it, we're going to call that a factorial. This is called a factorial. So I'm doing 5 times 4 times 3 times 2 times 1. You represent that with an exclamation point. So 5 factorial is the same thing as 5 times 4 times 3 times 2 times 1. And I'm going to prove that it's the same thing as 120 when I put it in my calculator. So let's do that. I'm going to enter my calculator by just starting with 5. I'm going to type 5 into my calculator. And then I'm going to go to the math button, you know, where you find the fractions. I'm going to scroll over to the top menu that says PROB or PRB, which is probability. And I'm going to click on the 4th one, which says the exclamation point. So on my page, on my screen, my calculator right now, it says 5 exclamation point. And when you press enter, you get 5 or 120. Anytime we're doing something with arranging, I'm just going to make a little note off to the side. I'm going to do this regularly throughout. If we are arranging in a line, you're going to do that number factorial. If I say arranging, you're doing factorial. How many ways can 9 people stand in a line? Well, that's just going to be 9 factorial. I'm only going to do it in the calculator once or twice. I expect you to know how to do it, but to me, the setup is more important. So make sure that we set it up appropriately. So 9 factorial is 362,888. All right. The next one is similar, but I'm not arranging everything in order. I'm only worried about the first, second, and third place. I'm only worried about the first 3 spots, not all 10 in order, just the first 3 spots. There's 10 people who were in a race, and we want to award first and second and third. So if I have first, second, and third, and 10 people ran the race, well, any one of those 10 could get first place. Once that person gets first place, now I have 9 options. I've got 9 people who could get second place. And then once that person gets second place, I have 8 options for third place. We're not going to call this 10 factorial because I'm not going all the way down to 1. We're just going to do 9 times 8, 10 times 9 times 8 in the calculator, and I get 720. So there are 720 ways for first, second, and third to happen. This is important because like if you get first place, that's different than getting third place. So that's why we have to take into account all of these options. That'll come back up later. So I kind of preface that. I'll come back to that later. Everybody doing okay so far? Okay. And the next one, Mrs. Ford has 8 jumpers and 10 shirts. How many different outfits can she make? So she has 2 things she can wear. She can wear 1 jumper and she can wear 1 shirt. She can't wear 2 jumpers. She can't wear 2 shirts, 1 of each. She has a total of 8 options for her jumpers. So she's got 8 options for the first thing that she has to choose. And then again, from the 1 t-shirt she gets to pick, she's got 10 options. So we're going to do times 10. We're going to multiply these together because those are like our options, just like we did above. We multiplied. These are all of our options that we're multiplying together. 8 times 10 is a total of 80 outfits or 80 options she has. Similarly, the next one is very similar, and these always have like clothing options. It's usually like this person has 5 shirts and 3 socks and 10 pants, and like how many clothes options. So whenever it's like clothes, we're just multiplying the numbers together. This time, Mr. Ford has 5 sports coats, 12 shirts, 10 pairs of pants. Assuming everything matches, so assuming everything can go, how many outfits can he make? We just have 3 numbers this time. We've got sports coats, 5, shirts, 12, and pants, 10. So 5 times 12 times 10 is 600. Any questions yet? All right, number 6. In how many ways can the home row of a keyboard be arranged? I don't know how many of you guys took typing, but that's like where your hands always stay. A, S, D, F, G, H, J, K, L. How many letters are in the home row? Can someone help me out?
9.
9, good. So we're arranging those 9 letters. This is just simply 9 factorial. 9 factorial. I'm not going to put that in. We put it in earlier, so you can find it if you need to. Okay, next one is different because we're not arranging anything. We're answering multiple choice questions. Or sorry, we're answering true false questions. There are 10 true false questions, and we want to know how many ways we can answer them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many options do you have for a true or false question? 2. Thanks, Brooke. Only 2. Thanks, Whitley. There's only 2 things. You can either choose true or you can choose false. You can't really choose anything else. So for the first true false question, you have 2 options, 2 choices, 2 ways you can answer it. Does the true false question from number 1 affect the true false question for number 2? No, right? We want it to. We want if you get too many falses in a row for that to make it the next one true, but that's not how it works. It could all be false. It could all be true. It could be alternating. We don't know what it is, so they don't affect each other. I also have 2 options for the second choice. For the third question, I still have 2 options. For all 10 of these options, I have 2 choices every single time. So we can put in our calculator 2 times 2 times 2 times 2, 10 times. Another thing we could do is do 2 raised to the 10th power. 2 raised to the 10th power. If you want to do that in the calculator, 2 to the 10th is a big number, 1,024. What if I change this and said, how many ways could we answer 10 multiple choice problems? And let's say multiple choice was our normal A, B, C, D. How would this change my problem or my answer?
Would they just be 4 instead of 2?
All my options would be 4 instead of 2. Very good, Brooke. So it'd be 4 to the 10th, not 2 to the 10th. And so like, and on, we could do that. So they're independent things. They don't affect each other. So it's just that number, however many times you do it. So whatever power. Okay. The next one, is very similar to the third one. So how many ways can a prize be awarded first, second, third? This one is how many ways can 4 different prizes be given out if there are 10 people in a contest? I know it doesn't say first, second, third, or fourth, but I like to think about like, okay, they're different prizes. So like maybe one's like a Starbucks gift card. Maybe one is like um a, I don't know, something like a cool shopping spree somewhere. And then maybe the last one's like a car. A car and a Starbucks gift card are 2 different prizes. So it matters whether you won like a Starbucks gift card or if you won like a physical car. So these are all different prizes. I can again put out my little dashes for my options. I don't know if I've said this yet. Teaching this a second time makes me like kind of lose my brains, but I've got like these little dashes represent my things that happen. So I've got 4 prizes. I've got 1, 2, 3, 4 prizes. And so I'm at kind of asking myself, the number on top is like, how many options do I have for each of those opportunities to happen, each of those events? So if I've got 10 people, any one of those 10 people can win the first prize. Once that person won, though, he can't win again. So then we have to go to the second prize. So now I've got one less, 9 people. 9 people can win the second prize. Once that person gets the second prize, she can't win again. So now we have to do 8 for the third and 7 for the fourth. Again, we're not doing a full 10 factorial. We're just doing 10 times 9 times 8 times 7. And I'll throw that in my calculator really quick. And that's 5,040. Okay. Any questions yet? All right, how many license plates are possible if they consist? Okay, then all of the rest of these on this page are very similar. Their license plate, it could be a phone number, it could be organizing any letters or numbers in a row. A call sign is like a radio letters. So if you listen to the radio, it'll be like, you're at, WFYI, that's the NPR station. That's what I listen to. But like your popular radio, so they have a little 4-letter call signal too. So these are all very, very similar. In how many license plates are possible if they consist of 2 letters followed by 3 non-zero digits? Okay, let's set up our opportunities again. I have 2 letters. I've got 3 digits. Letter, letter, digit, digit, digit. Now you have to just read the problem and you can't make something up. Unless they tell you it doesn't repeat, you can't assume that. Unless it tells you there are any restrictions, you just assume everything is okay. So I'm assuming that I'm looking at any 2 letters. Any 2 letters are there. So there are 26 letters in the alphabet, just in case you forgot. Sometimes I have to remind myself. You can choose any one of those 26 for the first letter. Now there's no restriction. You could pick any of those 26 again for letter number 2. They could be the same letter. They didn't tell us they couldn't be. Now for the digits, it's talking about non-zero digits. So if I think about non-zero, so 0 is the first digit, but then I think, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9 digits that are non-zero. The 10th one is 0, and then after that you get to 2-digit numbers. So if I'm looking at non-zero digits, it's 9. Again, there's no restriction, so I can have 9. I can choose any of those numbers for any of those 3 spots. 26 times 26 times 9 times 9 times 9. Anybody questions on that? Because we're about to do a bunch of spin-offs from that. So I can do 26 times 26 times 9 times 9 times 9. And I get this big number, 4,090. No, I'm too tired to do numbers today. 400,000, 492,804. Ooh, that was really hard. Okay, very similar for the next one. It says C number 9, so it's the same situation. 2 letters, 3 non-zero digits. But now it says no letter or number can repeat. So what would my letters be? How many options do I have for the first letter?
26.
Good. And then I can't repeat the one that I picked. So how many options do I have for the second one?
25.
5. Very good. Okay, now I'm going to do my non-zero digits. Again, I start with the same I started with earlier, 9, but now I can't repeat. So what are my next 2 numbers?
8 and 7.
7. Very good, Brooke. All right, I can multiply those really quick if I want. I don't know if I said this period or just thought it, but to me it matters more what your like setup is. So like that you did 26 times 25 times 9 times 8 times 7 versus like this number. That doesn't mean as much to me as the actual setup. So make sure that you show me the setup. All right, now I've got 4-letter call signs. So again, that's like WFYI on the radio. There's other 4 letters you can use for other radio call signs. But I've got 4 and they're all letters, so you can write little L's under them if that makes you happy. And it says how many are possible if every letter is allowed. It doesn't give me any problems. It doesn't say any restrictions, any letters allowed. We write 26 times 26 times 26 times 26. You can think of it as 26 to the 4th. I don't like to make a rule about the exponents because I can't remember that. And I don't want to just shove rules in my head. I just want to like see what's there. But since I see I've got 26 4 times, I can think of it as 26 to the 4th, which is 456,976. Okay, any questions yet? All right, the next one's the same, but it says how many are possible if no letter is repeated? What are my numbers going to be here?
26, 25, 24, and 23.
Perfect, Brooke. 26, 25, 24, 23. I'll prove a point by multiplying all of these out. 358,800 ways. The next one says, how many are possible if no vowels are allowed? Okay, I don't know what they teach you guys to be vowels anymore, but this is what I know vowel is: A, E, I, O, U. So I don't want any of those sometimes anything. There's just 5 normal vowels, so we're going to say that it's 21. Did it tell us about repeats or anything? It didn't say anything about repeats or any restrictions. It just says there's no vowels. So that means I'm going to do 21 times 21 times 21. Essentially 21 to the 4th. The last one is different, though. It says how many are possible if no vowels are allowed and no repetitions are allowed? What are my options there? What am I going to multiply here?
21, 20, 19, 18.
21 times 20 times 19 times 18. And that gives me 143,640. The reason I did all of these multiplied out was not because I want to show you that I know how to multiply in the calculator. It's because I want to prove a point. When we had no restriction and every letter was allowed and yes repeats and yes all these things and it doesn't matter anything, we had like 400,000 some. When I had restrictions with no vowels and no repetitions, I went down to 100,000. So I have a fourth of the options when I can't have vowels and I can't repeat than I had when I could do anything. All right, so I liked to group all of those together so you could see those are similar. Anybody have any questions yet? All right, let's keep rolling. Next page. If a baseball team has 9 starters, how many different lineups can we make? What am I going to do?
Would you just do 9, 8, 7, or what's the word, factorial?
Very good, Brooke. 9 factorial. I'm going to do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That was exhausting. So instead, we just say 9 factorial. There's no other restrictions. We just have 9 people. We want to put them in a line. Now we're going to do the same thing, but we're going to let the pitcher bat last. So I'm going to make a little dash here. 2, 3, 4, 5, 6, 7, 8, 9. I know I embarrassed myself the other day, baseball boys, because I didn't know how many people were in the outfield, but I can do this lineup, I promise. We're putting the pitcher last. I don't know a lot about baseball, but I do know there's only one pitcher in the mound at a time. There's only one pitcher who can start, so there's only one option for my last hitter. The pitcher has to go in that spot, and there's only one pitcher, so I only have one choice for that last one. If I know the pitcher has to go there, how many options do I have for my first spot now?
8.
8. Very good, Brooke. I'm minusing 1. So I had a total of 9 players, but one of them is the pitcher, and he has to go last. So I can't include him first. That means I only have 8 people that I can choose from for that one. And then now I'm just going to minus 1 each way down. So I've got 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Times. I know I've got 2 ones at the end, but 1 times anything is itself. So the 1 truly doesn't matter. This is the same thing as just 8 factorial. Because I had to move the pitcher to the end. He was in a designated spot. Everybody else could be in whatever order I wanted to. That is 8 factorial. The next one's super similar, but this time I'm not just having the pitcher pitch last. I'm having the best pitch or the best hitter go third. So I only have 1 pitcher. He's going to go last. I'm assuming the pitcher and the best hitter are different people because I have to go in different places in the lineup. So I'm also objectively, whoever the best hitter is, if they have the best batting average or if they hit the farthest, whatever it is, they have to go third. So in this third spot, I only have 1 person who's there, the best person. There's only 1 of them. So I put my pitcher in last. I put my best hitter in the third spot. Now how many options do I have for the first spot?
7.
7. Good job, Brooke. Only 7 now because I got rid of 2 of them by putting them in other places. So now I'm going to work my way down there. 7, 6. Ooh, I know that 1's kind of in a weird spot, but I still only have 5 for the next. 4, 3, 2, 1. Now I know it's a little bit funny out of order, but again, 1 times anything is just itself. So you can ignore the 1s. This is 7 factorial. So because I had 2 people that were in designated spots, I essentially did 7 factorial, 9 minus 2 factorial. Everyone doing okay? All right, let's keep going. Number 18, how many 1-digit, 2-digit, or 3-digit numbers can be formed using 1, 2, 3, 4, or 5, or 6? Okay, so we're gonna look at 3 different opportunities, 3 like events that are happening. 1 is a 1-digit, 1 is a 2-digit, and 1 is a 3-digit. So I've got digits 1 through 6. To make a 1-digit number, I have those 6 options, right? Just 6 options. To make a 2-digit number, I have to think about both places of the digit. How many options do I have for like my first digit in order for it to be a 2-digit number?
6.
Very good, Brooke. 6. And then I also have 6 for my second digit number. You don't have to minus 1 off because 11, 1 in the first one and 1 in the second one, that's a fine 2-digit number. 66, 6 in the first one, 6 in the second one, that's a perfectly fine 2-digit number. So I'm going to multiply those to get 36. And then a 3-digit number is the exact same. It's not just 6 times 6, it's going to be 6 times 6 times 6. Because 222 is a legit 3-digit number, even though there's a 2 in all 3 of my spots. So 6 times 6 times 6 is 216. Now, this is the only time today I believe we do this, and it does not happen a lot in probability, so I don't want it to get all mixed up in your head, but we are going to add these events together. So before, everything else we were doing was only like one event. Like how many lineups can I make? How many orders can I arrange a book? That's only like one thing I'm doing. I'm arranging books. That's one thing. This time I'm looking at 1-digit numbers or 2-digit numbers or 3-digit numbers. So I'm going to add these 3 numbers together. So 6 plus 36 plus 216. And that's going to tell me the total number of options I have for a 1, 2, 3-digit number that has digits 1 through 6. 6 plus 36 plus 216. And I get 258. All right. Anybody questions yet? All right. Let's do 19 and 20. It says, how many 5-letter words can be formed from the letters Chevy? Chevy. Anyone know what I do? We have 5 letters. We're arranging them. You do a factorial, 5 factorial. I'm not going to plug that in. I'm sure you guys know how to do it. I'm also going to do 6-letter words formed by the letters of 6 factorial. I'm going to skip these next two and I'm going to jump down to 24 and 25 really quick, or 23 and 24. This one now has bigger words. So those were 2 really small words, Chevy, PreCalc, pretty simple. This next one, how many 11-letter words can be formed from the letters of pre-calculus? This is a different problem than the ones that said like PreCal and Chevy, because do you see that I have repetitions of letters? I have a C that's twice. I have a L that's written twice. And I have a U that's written twice. Nothing else is repeated. No multiple P's, no multiple R's, no multiple E's, etc., etc. But I have all these repeated letters, so I need to take that into consideration. So we're going to do it like this. So when you have letters or beads or something or anything that repeats, we will do the total factorial on top, and then we're going to put all the repetitions on the bottom. So in this case, we have C is repeated, U is repeated, L is repeated. In this case, I've got an 11-letter word, so pre-cal. I've got 11 factorial. That's my total number of letters on top. And then I'm going to divide by the factorial of how many times C is repeated, U is repeated, and L is repeated. So C is twice. So I'm going to divide by 2 factorial for my C. L is written twice, so I'm going to divide by 2 factorial for my L. And then U is written twice, so I'm going to divide by 2 factorial for my U. Okay, what is happening here is that the repeating changes things, because when I just do 11 factorial, it's treating this C like it's different than this C. But if I rewrote pre-calculus out and was like, oh, well, I switched the C's, you'd be like, how am I supposed to know that? They're both C's, they look the same. So what we do is we divide by the 2 factorial to take out the repetition of the C's. We have to do it for the U's and for the L's as well. So if you have a question on that, please let me know. I could go more in depth with that, but that's as basic as we get. I'm only going to do this in the calculator one time just for sake of ease. Make sure to put parentheses around your denominator. So I'm going to do 11 factorial, so 11 math prob factorial divided by, and then I just want one big set of parentheses that has 2 factorial, 2 factorial, 2 factorial. Factorial, 2 factorial, 2. And then close your parentheses. If you don't do parentheses, it's only going to do 11 factorial divided by one of the 2 factorials and then times by the other 2. I got a kind of weird number, but I think it's okay. 4,098,000 or 989,600. Fine. All right, now we got to do the next one. Same idea, but just different repetitions. So see if you can write it out first, and I'll come join you in a second. Try that one. We got about 25 minutes here. Got halfway through class. All right, so Mississippi is another 11-lettered word, so I'm going to do 11 factorial. And then I've got 1, 2, 3, 4 I, so I'm going to divide by I or 4 factorial. See what else is repeated. S's are repeated. There's 2 and there's another 2. So I'm going to divide by another 4 factorial. And then the P's are also repeated. So I'm going to divide by 2 factorial here. Again, for sake of time, I'm not going to enter that in the calculator, but does anyone have any questions on 23 or 24? Okay. The next two, how many social security numbers are possible if all arrangements are possible, and how many telephone numbers are possible? Those problems are very similar to the license plate and the call number ones that we did on the front page. So we're going to think about that the same idea. I'm going to put out all my little blanks and see how many options I have for each one. Now, I don't know if when I was your age, if I knew my social security number as much as I do now. I use it all the time, it feels like these days. But it goes 3 digits, and then it goes 2 digits, and then it goes 1, 2, 3, 4 digits. So every person has social security number that looks like 3, 2, 4. How many social security numbers are possible if all arrangements are possible? So we have to think that we can use any digit with any repetition, with no restrictions, no nothing, because they didn't tell us anything. Now I'm going to assume that I can use 0. I'm sure there are rules with Social Security, but I don't know them. So we're going to assume that we can use all of the digits, not just 9. We also get to include 0. So I'm going to have 10. I get to use 10 for all of these. There's no rules on no repetitions. There's no rules on restrictions. I don't know if this is a thing that people will get, but I keep thinking of like this little like clapping game you'd play in elementary school, concentration, and they go no repeats or hesitations, and every time I keep saying no repetitions, it makes me think of concentration. So I hope somebody thinks that's funny and somebody gets that. If not, it's okay. I'm just too old for you guys, I guess. So 10 is what I have, and I have how many spots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 spots, so it's going to be 10 to the 9th. That's a huge number. I'm not going to put that in the calculator. The next one's super similar because it's talking about phone numbers are possible with the 317 area code. So if you get a telephone in Indianapolis, almost all of us have a 317 area code. And remember, your phone number goes 1, 2, 3 digits, and then 4. 1, 2, 3, 4. Again, I don't really know anyone whose first number is a 0, but like, let's pretend it can be anything. So any digit can be used anywhere. And there are, again, 10 options, 10 options, 10 options. It didn't tell us anything about restrictions or repeats or anything. So I have 7 spaces, and they all have 10 choices. So again, I can think of that as 10 to the 7th because there's 10 options and there's 7 possibilities that can happen. 10 times 10 times 10 times 10 times 10 times 10. All right. Everybody doing okay? Okay, the next one I think is kind of interesting and fun. It says, explain why at least 2 students must have the same first and last initial at Cathedral. Okay, let's think about initials. How many options do you have for your first initial?
26.
26. How many options do you have for your second initial?
26.
26, yep. I think there's a couple of you in this class that have it, like Hadley and Becca. You guys both have the same first initial and last initial, HHRR. So it doesn't really matter if you can't -1. Whitley 2, Whitley Welton. I'm trying to sorry if I didn't call anybody else out. But some of you guys have the same first and last initial, so it can be 26 times 26. And so I'm going to multiply those together. I have 676. 676. Now, we have way more than 676 students here at Cathedral. We almost have twice that, I think. So that means that there has to be at least 2 students just based on numbers, based on like how things are working out, based on probability. We have to at least have 2 students that have the same first and last initial. I can't promise every single one of you has a match with somebody, but at least 2 people have the same thing. All right. These next 2 are very similar. And this is where I'm going to talk about a permutation and a combination. It matters on which order you pick things, okay? So I'm going to read 26A and B, and we're going to think about how those are different. So 26A says, in how many ways can a club with 20 members choose a president and a vice president? And then letter B says, in how many ways can they choose a two-person governing council? Okay. Two-person governing council, president, vice president. It matters on the first one. If I pick somebody to be a president, somebody to be a vice president, that matters. So like right now I see Brooke and Gabby. So like let's say I pick Brooke to be president and Gabby to be vice president. Is that different if I made Gabby vice president and Brooke, if I made Gabby president and Brooke vice president? Yeah, right? You'll have different responsibilities depending on which job you take. So if you're the president, you may have like more things to do or you have to talk to more adults, and vice president maybe is in charge of like logistics or taking notes at meetings. If I put both Gabby and Brooke on a two-person governing council, does it matter if I'm like, my council is Brooke and Gabby versus if I said Gabby and Brooke are on my council, right? It doesn't matter. They have the same job. It's like captains on a team. You're both captains. Your job's the same. It doesn't matter which one's which. So I'm going to introduce the word permutation. I think it's just spelled like this, permutation. And this is where the order matters. And it's usually because it's specific things. It's like who wins first, second, third place, who is president, vice president, who is like your maid of honor versus just a normal bridesmaid. Like this is where it matters. Like you have like a title essentially. The other one is called a combination. And order doesn't matter. All right, no order. That's like picking a group of bridesmaids. It's like picking two captains for a team. It's like picking three people on like the executive board of something. Like it's like you all have the same job. Nobody's more important or less important than anybody else. The way we represent it is using P's and C's. So permutation is a big P. You do the total number in front of the P, and you do how many you're picking after that. So of 20 people, I'm going to permutate in a way that order matters 2 of them. I will not make you do it by hand, but you can think of it by hand by doing 20 times 19. Because I had 20 options for the first spot, and then once I pick one, you got 19 for the second spot. So 20 times 19, and I've got 20P2. I read that 20P2. The next one is two-person governing council, and it's a combination. So we're going to use a C to represent combination, and it's still 20C2. This time I'm choosing 2 people, and it doesn't matter what order they go in. I will not make you do this by hand, but it's the same as before. It's 20 times 19, but it's divided by 2. Because if I choose Gabby and Brooke versus Brooke and Gabby, it's still the same people, and it doesn't matter which order they're picked in, so we would divide by 2. Again, I won't ask you to do it this way. It just, if anybody wants to think about it that way, you can. Let me show you how to do it in the calculator. That's what I'm sure you guys want to do. I want you to type 20, and then I want you to go to math and your PRB menu under math. We just spent a lot of time using the factorial number 4, but number 2 says NPR. NPR. So I'm going to click that. My calculator is a weird notation, so I have to like enter it in 20P and then 2. If you have any questions on how to enter it in your calculator, please let me know. But when I do 20P2, I get out 380. So if you don't get 380, talk to me at some point. Got like 10 or 15 more minutes, sure. Same thing for the C. I'm going to do 20, but I'm going to do the third option, which is NCR. So C for combination, P for permutation. I'm choosing 20, choose 2. And I get out 190. And I'm going to prove to you that 20 times 19, the P is 380. And if I take that number and divide it by 2, it's 190, which is what my C is. So I'm proving to you that the by hand works. All right, everyone hanging in there? Next one is very, very similar. It says, in how many ways can a club with 13 members choose a 4-person leadership team? And the other one says, in how many ways can a club choose a president, vice president, secretary, and treasury? I want you to think about which one's C and which one's P. Which one does order matter? Which one does order not matter? Leadership team versus president, vice president, secretary, treasury.
A is C.
A is C. Good, Cleva. It's a leadership team, right? It's C. It doesn't matter if you're first one on the leadership team or the last one. You all have the same job. This one's a C. So I'm going to write it as 13C4 because it's 13 is my total number of people I can choose from, and I have to pick 4 of them. And that makes B what? Anyone know what B is going to be? It's going to be P. I can't tell if you guys just don't know if we're just saying it in our heads and writing it on papers. So I'll throw it in the calculator just so you can check your work. I'm going to do my C first. So I'm going to do 13C4, which is 715. And then I'm going to do 13P4. And that's a much bigger number. When you do permutation, it's often a bigger number because it matters what order it's in. And so it's different if like you get picked first or second. But when it's combination, it's often a smaller number because it's just any combination, any grouping of those people. It doesn't matter what order they're in. All right, let's keep rolling. Everybody with me? Okay. The last thing that we're going to look at today is organizing in a circle. So I'm going to put this in off to the side. I guess you could also say arranging. So I used arranging earlier. We're still arranging, so we're still going to use factorial like we did earlier. But when we arrange in a circle, it's a little bit different. I could prove this out to you separately, but if it's in a circle, we don't really have class time for me to go through the whole process, but it's in the way that it rotates, and since it's kind of a loop next, you need to make sure that it's not the total number of things that you have, it's -1 factorial. So like, for example, if I had 8 people sitting like in a row on a log, then like that would be 8 factorial. But since they're around a campfire, which is a circle, the way that the circle works, we're going to do 1 less than 8. So we're going to do 7 factorial is going to tell me how many ways 8 people can be seated around a campfire. 7 factorial. Number 29 says, in how many ways can 10 people be seated around a circular table? So 10 people at a circular table, it's going to be -1, so it's going to be 9 factorial. Okay. Number 30 says, in how many ways can 6 keys be arranged on a key ring? Well, I don't have a key ring to show you, but I'm going to just use my hands. What happens when you have an object like a key ring or like a bracelet or I don't know, something that's in a circle that you can physically like pick up and flip around, there are going to be reflections. Like if I'm looking at my hand, I know it's not a key ring, but it's my hand. My hand has the fingers arranged in this order: thumb, pointer, middle, ring, pinky, whatever. Welcome back to kindergarten. My hand is arranged this way. What if I reflected it? What if I flipped it? My fingers are not in a different order, right? I didn't like take my thumb off and put it in a different place. It's still in the same order, but I just flipped it. And now it looks like it's in a different order. Now it looks like my pinky's first, blah, 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 and my thumb's last, versus before when my thumb was first. When that happens like this with a key ring or a necklace or a bracelet, we have to deal with the reflection. So it's not just the fact that it's going to be not 6 for my keys, but 5 factorial. And then I'm going to divide by 2 to get rid of the fact that like this is the same as this. So I have to divide by 2 because 5 factorial is going to give me all of these options and I only want half of it because this is the same thing as this. And the way 5 factorial is treating these 2 as 2 totally different options. So I'm gonna write 5 factorial divided by 2. Anybody have any questions on that? Okay. All right, let's move on. The next one is talking about these necklaces, and it says how many necklaces can be made from one blue, one yellow, one green, one orange, one pink, one purple bead. Okay, those are all very independent colors. Nothing's the same. There's no repeats there. So there's a total of 1, 2, 3, 4, 5, 6 beads. So I've got 6 beads, no repeats, no nothing. If the necklace has a clasp versus it has no clasp, a clasp is, the thing that like connects so you can take it on and off. If it has a clasp, then we can treat it like it's a line, right? You can undo the clasp and then you hold your necklace out. It's like a straight line. So I like to think that this makes a line. And so I'm going to do my 6 factorial because I have a line. But when I connect it, it becomes like that key ring where there's a reflection. So I'm going to have to divide by 2. So if it has a clasp, I think of it like it's a line, but I still have to deal with the reflection, divide by 2. If it has no clasp, then that means it's a true circle because it never opens up. It's always in that kind of rotation no matter where you're at. So I have to treat it like a circle. I have to do 5 factorial and still treat it like the keychain where it's reflected. 5 factorial divided by 2. So no clasp is like a circle. So we're doing n minus 1. Again, I'm not putting these in the calculator, but you're welcome to. Okay. Let's see if we can do the last one. So no clasp versus clasp. I've got a circle and I've got a line. What I'm going to do right here is I'm combining the idea from the like letter problem, and I've got some repeats. So let's think about how many total beads I have, and I'm going to divide by the repeat. So I've got 2 plus 3 is 5, plus 1 is 6, plus 4 is 10, plus 2 more is going to be 12. Okay, it says the beads of each color are alike. So that means like the 2 blue beads are identical. They're not different, they're the same. So I've got 12 beads total. So if I have no clasp, I know that's the bell, but I'm going to finish up because you guys are all at home and we don't have to clean up in this class. With no clasp, it's like a circle, so I have to do my n minus 1. So I'm going to have 11 factorial on top. And then on bottom, I have to get rid of my repeats. So it looks like I've got repeats with the blue, so I'm going to divide by 2 factorial. I've got repeats with the yellow, so I'm going to do 3 factorial. I only have 1 green, so I don't have to deal with that. I do have 4 oranges, so I have to divide by 4 factorial. And everything else is unique in 1. The only other thing I have to do is I have to deal with the reflection like we did above, so I also have to divide by 2. So I've got my factorials for the repeating. These are the repetitions, and then this is for the reflection. So my total is on top, and I had to divide by my repetitions factorial and my reflection. It is almost the exact same for the last one. Does anyone know the one thing that changes for the last problem?
It would be 12 instead of 11.
Perfect, Brooke. It's 12 instead of 11 because with a clasp, I am able to make it into a line. So 2 factorial, 3 factorial, 4 factorial times 2. Okay. That is all I'll make you stay online for because I don't want to get too far ahead of the other class. We did a couple more problems on them, so hopefully we'll get them caught up tomorrow. We're going to finish anything I want to finish from 9-1. We're going to do as much as I want to from 9-2 tomorrow. And then I also want to kind of look at what chapter 7 is going to be for review because we're testing early next week on chapter 7. So we can put that behind us and continue on with chapter 9. We only have 2 more weeks of class. And so we really have to buckle down. And that's why I'm kind of rushing through this stuff. I'm getting as much as I can get done, but that's where we're at. So we're going to push a lot in tomorrow. So make sure that you're ready to go or that you're ready to practice some stuff on your own so that you're prepared for your test later. I'm going to stop sharing. I'm going to stop recording.